So on page 74 of Sheaf Theory through Examples, there's this notation that comes in. So there's this diagram that are shown, which is characterizing in the category of elements, although I don't think he's using that term here, a particular pre-sheaf. Right? This is this idea of this pre-sheaf that we spoke about on the board, but it's basically a single object and this next morphism, right? And what he's showing is a set of possible states. So that when you map that over to set, you get a set. The single object maps to a single set of states. And the next morphism tells how the states evolve, what state evolves to what next state. So it maps a given state to its, it's a function, right? Morphisms in the schema category turn into functions. And function is from the set to itself. So it says it's a function from the set of states to the set of states is what that morphism in the schema category gets mapped into instead. Morphism or function from the set to the set of states to the set of states. And it specifies, therefore, for each state, what the next state is. That's why it's from states to states. Right? The morphism in the schema category goes from single object to the single object, and that object's mapped in states. So now it goes in the set category from states to states. And what's shown here is the category of elements of that functor, because what's shown is like it maps A to B, and B to C, and C to D, and D is just mapped to itself from then on. And E is mapped to F, and F to D, and G and H are just mapped to each other, and I is just mapped to itself. I'm not sure why I is not listed in the set of states. It should be. But notice it says where it talks, where sigma, this is this morphism, next morphism. It acts on the figure A. And notice he says star labeled with A, this mapping. See that? Star, arrow, X.
Sorry, which page?
Page 74. 74.
3 lines below the
3 lines below the image. There's this arrow from star to X. Do you see that?
Oh, yeah.
Labeled A. What that is a map from the representable for the star into X. That's why it's into X.
Yeah.
And that representable picks out a specific state. Right? That's what representables do. They pick out a specific, according to the Unity lemma, they pick out a specific one. They're in one-to-one correspondence. These maps from the representable for star into the pre-sheaf X are in one-to-one correspondence with that functor applied to the state. In other words, the set of states. So there's one of these for each state. And this one, he's saying it's called A.
Mm-hmm.
It's the A one. So he's saying A can be thought of as as this functor from the representable to the pre-sheaf X. And notice he has this, just as Jeff says, he has this footnote. he says, incidentally, the notation star to X labeled A will be fully justified by the unitative results, looking at chapter 6. And so that's why it's called A. There's another one, B, that is a different functor mapping from the representable for star, finding the representable for star in the pre-sheaf X. And that's called B, right? And this morphism X, this is the pre-sheaf applied to the sigma, to the evolution map, takes the particular star figure named A to the star figure named B. So it maps the state A to the state B, but it maps the thing found for the first one to the thing found for the second one. It maps them from one to the other. He's saying it's a mapping by extension between these functors from stars. So we have this here. Maybe I'll put it down here so it's a little more visible. Here we have a little schema category. And here we don't have to worry about op here because op just flips around. It looks the same. Yeah. And this is set. This guy goes to some set here, which is A, B, C, to I, although he leaves it out. And this is the function corresponding to next, which according to this diagram clearly maps A to B and B to C, I think. And both. But the point is, he's calling A here. He's taking advantage of the pun, as it were, that if you have the representable per star, like as a C set, right? This is a functor here, right? This is a functor F. And if I have the representable, well, he calls it if I consider the representable in this category, I don't know, for star to other things, if I have that, this representable, what would it map star into? A set of size what? This is the schema. The representable, what size set will this be? One. Actually, wait.
Where there's no identity.
There's identity. There's identity. There is identity. And in fact, it's not just identity. What else is there? Is this really one? Think back to free. Think back to free. Is this one? Is it? Oh, sorry. No, we have identity. Identity will be one. So we know it's more than one. And we know it's at least one.
Next composed with next.
Next composed with next, composed with next, composed with, and what I was telling you before is that it's a freely presented category. This is just a free presentation of it, meaning next squared in general is different from next. Next cubed is different from next squared, different from next. So this actually has natural numbers, right? In general. So indeed, okay, this is the plot thickens. So if we were to map this in to this, okay, this is getting more complicated. if we were to find a homomorphism, okay, from a functor, well, it's a natural transformation between these two guys, a homomorphism from this C set to this C set to this C set, really. Sorry, it's really between these two C sets. Yes, so this is mapped to this is a C set. Maybe I should map it, show it. Maybe just to be explicit, we'll show the schema category again. Maybe I'll just draw it like this. This is a different functor. This is the representable functor. Right? And this maps this guy into natural numbers. And next, what does next do? What do you think it does? Well, it's a functor. So what does it have to turn? It has to turn this into what here? This is a function, right? This is a set. This is a function. So what function does identity have to turn into? What function? So I'm telling you, star turns into natural numbers because there's one for every 0, 1, 2, 3, 4. There's a natural number of times. There's a set for each of the natural numbers of times you can get to here. What does it turn next into? Oh, sorry. This functor, what does it turn identity into? To the what function? It's gotta turn it into a nice function. What's like the nicest function? Well, you might think it's boring, but from the natural numbers to natural numbers. It's got to be a very distinguished function. Add 0. It's just add 0. It's add 0. So identity turns into the add 0 function. In other words, identity, right? On natural numbers, right? Right? Identity on natural numbers. What does next turn into? Sorry, what does one iteration of next turn into? We talked about it last time, actually. What does it turn into?
Add 1.
Add 1. What does 2 next turn into? Add 2. What does 3 next turn into? Add 3. Right? Which is, it has to be, because like you can either compose here and then map over, and you have to get the same result as composing here. Sorry, mapping over and then composing. So let's walk this through. So if I compose next and next here and map over, what I'm telling you is I have to get the same thing. It's totally determined as if I map next over, what's next here, add 1. Map next over, add 1, compose here, add 1 is add 2. So I'm telling next squared has to turn into add 2. Next cubed has to turn to add 3. Okay, now, given this, okay, so this is our representable. That's one big honking representable, I'll tell you that. That's a big representable. Okay. Don't ask CatLab to like derive that representable for you.
Why? Why CalLab cannot?
Actually, CatLab might be able to, because it might. I think it will just diverge. I suspect it will diverge. I think it's not smart enough to realize like this is just the function iterated that many times. It's a good question. Anyway, so if I had this and I have to have a mapping now from this to this, oh goodness gracious. Oh gosh. And I'm telling you that there's one of these for every, there's a mapping down here. Of course. Yes. I think that's right. Hmm. I think there's going to be a mapping down. All these different mappings down, so all these natural transformations down. Save, domain, codomain. C, set. And what I'm telling you is actually, I should draw it this way. Separate natural transformation for each of these. That is a separate mapping down. Where I think each of these natural numbers. Oh gosh. Oh gosh, that's beautiful. Oh gosh, that's beautiful. Oh gosh, that's beautiful. Oh, that's really interesting. Do you see what that does? That is the coolest thing. Each of these mappings is determining for each time, this is time here. This is serving as time. Time 0, time 1, time 2, time 3, time 4, time 5. And each of these is determining for each time point which state you're in, subject to this rule. Basically, it needs to, yes, okay. So okay, so that's really interesting. It's like for each time point, time 0, time 1, time 2, it has to be in a particular state, right? But more than that, if you do next here, you go to the next time, it has to commute with next here. Like if you do next here, you go to a new time and you map over and you map down to that appropriate next state. It has to be the same result as if you map the current time t, take this and get to the next state. So what I'm saying is like this natural transformation, call it alpha, has to be such that like if I'm in state t, right, so it needs right, it's going to map the elements of these sets. Okay, wait a minute. Something is not. Yes. Okay. Right. So what is this going to look like? It has to have a mapping between this to this. Okay. I think essentially what has to happen is that it has to have a mapping such that if you map over the value at time t and then do next here to map it to the next to the value at time t plus 1, that's equal to going to the next time and mapping over, which it needs to essentially be a mapping which honors the rules of evolution of this. Here. I think that ends up being correct, I think. Right, we need to, there's the naturality triangle here. And the naturality triangle is going to have what things in it. This is set. So the naturality triangle, we're going to have this schema to set. This is in the naturality triangle. Sorry, naturality square. Okay, so we either have to have, let's call this function x. This functor x. Call it x. So we can either have where, so this thing, okay, maybe it's not even going to be a full square. So we have to have what x maps it, x maps star. Oh, this is going to be gorgeous. Or where this one maps star. Like that. Look at that. Look at that. That's where it maps it, which is equal to natural numbers. This is all natural numbers. Look at that. Look at that. You see that? Watch this. Watch this. So this maps star to here. This maps star to here. And we have to relate them in a way that's natural. What do we mean by that? We mean that for any morphism that goes from this to another object, well, there's no other object. All there is from this to itself, right? Here, from this to itself. This is a set of states to itself. This is a set of time to itself, right? Do you remember the naturality square? Do you remember naturality square? Just to make sure we're on the same page. Where am I going to put this? Where am I going to put this? I'll put it over here. Okay. You remember the naturality square? If we have here, so if we're going to have here, these are, if we have our source category, here we have our source category. And call it A and B. And we have some morphism. We okay with this? And we have two functors, F and G, that go from the source category to the target category. This is F. This is G. Remember that? Remember that? This is where F maps A. This is F of A. Right? Remember, the natural transformation translates from where F maps things to where G maps things, but in a way that's natural. That's not just willy-nilly, it's natural. So this is where G maps A. And this here is alpha sub A. It's a morphism in this target category that translates from where F maps A to G of A. That has to be the same for any morphism F from A to B. So here we are, F. But this is not just F. It's the lifting with F, where F, the function to which, for example, in our case, it's F, where F capital, the functor maps F. Maybe I'll call this, if it's okay with you, I'll call it something else here instead of F, just to avoid too many F's. I'm going to call it H. H is good. I'm going to call this H. Are we okay with that? We okay with that? This is G of B. And this is where F of B. F maps B. Are we okay with this? Oh my goodness. Oh my goodness. What is this one here? Yeah. G of H. So G, we need G to play nicely. So if we consider how G handles H, and how this is H here, and how F handles H, they have to handle it in ways that are compatible at some level. So it's well behaved. So there's a natural transformation, very special thing. Call it alpha. That goes from F to G. If we have this very special case that, look, so So we consider where F maps A and B, and link and the morphism to which it maps H, and where G maps A and B, where morphism to which it maps H. And there has to be these morphisms in this category that are there, that are the same for any H in the source category, that go like this. So alpha sub A and alpha sub B, such that this triangle commutes. There has to be this nice thing that either you can map it over with F, map it from A to B with F, and then translate it over to G, or you can map it with F, translate it to G first, map it over with H via G, that G's version of H, and you have to get the same result. Remember that? We did it for like, if you have a list, you can either take the head to a safe head on it, get a maybe, and then apply the operation of interest H to that maybe, lifting it to apply maybe, F mapping it for maybe, or you can do mapping it on the list and then translating over to the maybe. And you have to get the same result. So that's our naturality square. And all I'm doing is I'm creating that naturality square here. I'm creating it here. Are we okay with this? Are we okay with this? Okay, so watch this. I'm trying to create that naturality square, but it's kind of degenerate because there's only one object. So like the top of it got squished, right? And I mean, maybe I'll draw it out as a square just to make it directly parsable as such. So here we go. Here we go. That's empty. I'll have it now. Here we go. So that's where that object, this is some set. It's called, it's natural numbers. That's what I'm telling you. Natural numbers. Set of natural numbers. This is this set. And what I'm telling you is, okay, so where is this going to map? What is this thing? This functor, what does it map next to? Next is our function H here. Next is our function H over there. That there. Morphism H. But what does it map H? Oh boy. So H is next. So this is also N. This one is N. This one is also X sub star, because there's only one object. So this thing is always going to go between. And so this is going to be how this thing maps next. Okay. That we already said what it is. We'll get to that in a second. This will be how it maps next, which is going to be the sort of, I'm going to call it next exclamation point. It's sort of how the dynamical system evolves as a function. A goes to B, B goes to C, C goes. What is this thing? Oh, this is the most beautiful thing. Oh, this is the most beautiful thing. What does this do? It increments time, the current time to be times t plus 1 is what this one does. What does this one do? This one maps. I'm going to call it, what am I going to call it? Well, I'm going to call it the value of the discrete dynamical system at time. It's going to map, it's a function. It's going to map each of, right? It's a function from this set to this set, from natural numbers.
Just say the added time to you.
Yes, exactly. Exactly. maps each time into the state at that time. Maybe I'll at the cost of being long, I'll just say state at time t. Okay,
Mm.
okay. And what I'm telling you is to commute, what this has to do, if we take a state and we do next of that state.
Plus actually is a
Yes,
time
yes.
plus
yes,
one, next state.
Yes, yes,
It's naturality.
that's right. That's right. So this is saying like, if you take time t and I map it to my state here, to the current state, okay, B. And then I evolve it according to this. So maybe B goes to C. That you can look at the diagram of page 74 of sheaf theory, for example. B goes to C, right? B goes to C. Here, that has to be the same as taking the current time, adding 1 to that time, and then going to the state at that time. So this function notice this is the same object, so this has to be the same function here and here. And there exists a mapping here for each such function. And what I'm telling you is that there's only one such function, actually. The function that maps each to its state at that. So it identifies the function that says how this system evolves. Okay, so what Daniel Rosiak is saying in this book, he's calling got it. Okay, so what he's calling star, he's saying A, he's calling A, his name for A. Steve sheaf theory, for example's name for A, for state A, is star X. And why? I thought I had it. Aha. So what this is saying, though, is that okay. That the Oneida lemma tells us that these maps are in one-to-one correspondence with this set of states. what the Unita limit's telling us. So this is X. So X of star here is like A, B, C, D, I. Because I think here. What this is saying is that there's, and I need to understand this, that there's one such map. There's actually, I thought there was just one, but there's one such natural transformation.
So can we say that for any next in the C set category, any function next in the C set, we have only one next in the representative one. For each function next in C set.
Well, that's what I thought, but what Unita is telling us is that X of star, the thing to which is in one-to-one correspondence with the number of morphisms in the category C set, as you said, and these natural transformations from this to this. And I think if I need to think about this, but I think because this will fully specify, so this only occurs if it's fully consistent with this. But somehow it's saying there's one of these for every one of these states. And I'm trying to understand why that is. Is it because in every one of these states, it could be steady state? No, I don't think so. Well, maybe that is it. Maybe that is it. Maybe that is it. Right, look, if you have only one state, there's only going to be one function in, or one natural transformation in. There's only one choice because that state has to go on forever. Right? There's only one state. There's only one possibility, namely you stay in that state. Map pins. If there's two states, there's I think there's guessing that this is because there's two possibilities that you need this to hold, but there's two different ways it could hold. If it, I don't know if this is correct, but you could stay in. I mean, this is natural number of things. So like you're going to go through each of the times and it's got to stay either in A. Ultimately, it has to fall either in A forever or B forever. That's not true, right? It could go back and forth. It could go back and forth forever. So that's actually not true. I was thinking it has to steady state behave. Yeah, but it could go A, B, A, B, A, B, A, B, right? So that's not true. So that argument breaks down. I got it. I bet it's the initial state. It's the initial state. It's the dumb initial state. It's the stupid initial state. That's all it is. That's why it's one-to-one correspondence. This picks out which one you're going to start in. And after that, it's totally determined by this. That's the degrees of freedom. There's one map. It's got to adhere to it after the initial state. And the only question is which one you start in. And this specifies you could start in A, you could start in B, you could start in C, you could start in D, all the way to I. Each of them has a mapping in. If you start in that state, there's a mapping in that's consistent, that as you evolve after that for each time. 0, 1, 2, 3, 4, 5, 7. But there's one mapping for each state you could possibly stay in. There's one consistent mapping. If you start in A, this will be what plays out. If you start in B, this will be what plays out. If you start in C, this will be what plays out. Start in D, this will be what plays out. After that, it's totally determined by next. But it's next does not determine what's the initial state. And this map, I think, totally gives you, it's a one-to-one corresponds to these because it just picks out which one you started. That is wild. That is wild. Wow. Okay. Okay. That's gotta be it. That's just gotta be it. And it makes total sense, right? Like this forces it to be consistent with this once you're in the system. The question is, where do you start in the system? And if you start in A, it forces you to be consistent with where you start in B, A, B, blah, blah, blah. Notice, yeah. Yeah, because you could have something if you start in A that's consistent with next. You could have something that starts in B, it's consistent with next. If you start in C, there's something that's consistent with next. But they're different things. And these natural transformations pick those up. Okay. I'm sorry, I hope that wasn't too confusing, but I think this is an interesting little example.